That is what? Vector subspaces. So what is vector subspaces? Let's first go to the definition and then I'll give few examples. So let V be a vector space. So the vector space means a non-empty set which has few properties which we have already done in the last lecture over a field F. So I'll say field F, but in our course, our field will be restricted to either real number or complex numbers, right? Now, assume that, now let W be a subset of V, then W is called the subspace of V if W itself is a vector space over the same field F.
So in other words, W will be a subspace of V if W is a subset of V, and W should itself be a vector space. That means it should satisfy all those properties of vector space.
What could be the possible subsets of V? I mean, there are two trivial subsets of V. One is what? V is a subset of itself, right? V is a subset of itself, and 0 is a subset of V. So these two are always the subspaces of V. These two will always be subspaces of V. So there is a small important result, that is what? So there is a theorem that says what? If W is a non-empty subset of a vector space V, then W is a subspace of V if and only if W is closed under addition and scalar multiplication, right?
We will not go into the detailed proof of this theorem. We shall draw only a rough sketch.
To see this, so there is, let's say, I mean, this is the if and only if condition. That means what? That says what? Ki W, if W is a subspace of V, then you don't need to prove every property of the vector space. So W is called the subspace of V if and only if it is itself a vector space. But what we do in generally in proving the vector space, let's say if we want to prove that some set is a vector space over R or C, then we have 8 to 10 properties which we prove for each example, right? But in case of subspace, we have shortcut, and that is what? Because W has an advantage that W is already a subset of a vector space. So it needs to satisfy fewer properties, and that's what you just need to prove that W is closed under addition and scalar multiplication. That will be sufficient to prove that whether W will be a subspace or not, right? So see this, how it works. So let's say it's an if and only if
Condition.
So suppose that W is a subspace of V. So what do you mean by subspace? Yes, tell me. What do you mean by subspace? What should be the qualification of W to be a subspace by definition?
It should be a vector space over same field.
Yes, it should be a vector space and it should be a subset of that particular vector space.
Yes, sir.
Is that fine? So first of all, W should be a subset of V, right? Always keep in mind, if W is a subspace of V, that means W is a subset of V and W is itself a vector space, right? Right. So suppose that we are given that W is a subspace. Now we want to prove this fact that W is closed under addition and scalar multiplication. First of all, given is W is subspace, and we want to prove this fact. Okay, so see this. So now, if it is given that W is a subspace, so by definition, W is also a vector space. Yes, are you with me on this? So if W is a vector space, we know that all the vector spaces are closed under addition and scalar multiplication. So therefore, by definition of vector space, W is closed under addition and scalar multiplication. Are you with me on this?
Yes, sir.
So the first part is really easy, right? Now, second point is bit lengthy. Now we are given that W is a subset of a vector space V, and W is closed under addition and scalar multiplication. Now, what do you want to prove? We want to prove that W is a subspace. It is already given that it is a subset. We need to prove that subspace. Subspace is something more than the subset. What extra it possesses, it should be a vector space, right? So हमें ये prove करना है that we want to prove that W is a subspace. That means in general we want to prove that W is a vector space. Are you with me on this?
Yes, sir.
Yes,
Now
sir.
the problem is it satisfies only two properties, and the rest of the properties should be proved by us. Okay. So first of all, it is given that W is closed under addition and scalar multiplication, and it is non-empty subset. I must write it as W is a non-empty, right? So let X, Y belongs to W. So it is given that your X plus Y also belongs to W and alpha X also belongs to W. For all alpha belongs to R or C. Let's for the moment assume that it belongs to the R, right? So these two properties are given. So let's see, we want to prove first property of associativity, A1. So if X, Y, Z belongs to W, you need to prove that X plus Y plus Z should be equal to X plus Y plus Z. Will it get satisfied? Yes.
Yes, sir.
Why is it so?
Sir, because the vector space is same.
सीधी बात ये है कि जो x y z w को बिलोंग कर रहे हैं वो v को तो बिलोंग कर ही रहे हैं, because w is a subset of v, right? So since w is a subset of v, so therefore these x y z also belongs to v, and since v is a vector space, so if it is a vector space, so all the properties of vector spaces are getting satisfied. So that means x plus y plus z must be equal to x plus y plus z. Yes, you're with me?
Yes, sir.
Yes, is it fine? So basically it is carrying the properties. See, x, y, z are going into the w, but it has already a properties. Just because of the blessings of v, they are already satisfying the associativity law. So if they are sitting in W, they'll also satisfy the same law.
Yes, sir.
Yes,
Okay.
sir.
Now see this. Now, if you have X belongs to W, so it is already given that it is satisfying the scalar multiplication rule. So in particular, if you take alpha to be equal to -1, so therefore minus X will also belong to the W, right? And if you add x and minus x, it will always give you 0. Why? Because if X belongs to W, then X also belongs to V. And if minus X belongs to W, then minus X also belongs to V. And we know that if X and minus X are belonging to the V, then their addition will be nothing but it will result in additive identity, right? Is it fine? Yes.
Yes, sir.
But see, here the property we are applying that scalar due to the scalar multiplication, minus X should belong to the W. But if X belongs to the W and minus X belongs to the W, then
W
has another property. That's what it is closed under addition. That means the result of X and minus X should also belong to the W. That means 0 should also belong to the W, right? Is it fine?
Yes, sir.
That is because of addition property, closed under addition. Right? You're with me? So that means 0 also belongs to the W. So
we want to prove that
W is a vector space. So it must has each and every property of the vector space. So now it is also having the identity which we have proved. Why? Step by step. Since it is closed under addition, so alpha X will belong to this. So we'll choose a particular value of alpha minus X should belong to W. Now it is also closed under the addition. So X plus minus X, whatever it is the result, it should also belong to the W. But since your X and minus X whenever belong to the V, their addition their addition will generate identity element. And that means that identity element is in W. So that means identity is possessed by W. W is having identity, right? So that means the second property is also satisfied, right? Is it fine?
Yes, sir.
So similarly, you can prove the rest of the properties. I'm not proving them, I'm just telling you. So similarly, you can prove the rest of the property. Let's say for A4. Now see, actually this properties are for A2 and A3 as well. See, we have proved that inverse part as well, and we have proved the identity part as well. Both of the things are there in W. You want to prove that A4. That means you want to prove that whenever your X and Y belongs to the W, X plus Y should be equal to Y plus X. So is it true or not? Bolo?
Yes, sir.
Yes, sir.
Kaise?
Sir, if X, Y belong to W, it also belong to V.
Yes, CD baat, because it has certain features. Because XY also belongs to the V, right? And X plus Y is equal to Y plus X in V. And X plus Y is equal to Y plus XY because V is a vector space. So the same nature will be preserved by the W as well, right? So similarly, you can prove the scalar multiplication property there. Is it fine? And there is one more theorem, which is actually the combination of, this particular theorem. So I'm just stating this theorem. I'm not going to prove this. So a non-empty subset W of a vector space V is the subspace of V if and only if whenever alpha and beta belongs to the real and X and Y belongs to the W, alpha X plus beta Y should belong to the W. Right. So can you connect this property? Can you connect this theorem with this theorem? Yes. It is closed under addition and scalar multiplication. And this theorem is saying what? The theorem which we have stated right now, this is saying what? This is saying that alpha X plus beta Y should be equal to W. So is there any similarity between these theorems? Is there any similarity?
सर जो उसमें कंडीशंस थी उन दोनों का मिक्सचर है.
Combine करके कर दिया गया. Yes, you are right in saying this. See, the scalar multiplication part is there, right? And the addition part is here. So basically we have combined those things, right?
Yes, sir.
So we've written the fact in just one statement. So now, most of the time, we'll be checking, most of the question will be based on the idea that whether a particular subset is a subspace or not, right? So we are doing a lot of exercise on that. So see this. Show that so we'll prove those two properties, right? So let's pick an example. So pick two elements of there. That means pick, let W1 and W2 belongs to W, right? So how W1 will look like? Yes. How W1 will look like?
X1 comma 0.
Yes. So W1 will look like a tuple X1 comma 0, and W2 will look like something X2 0, and X1 and X2 both are real. Okay, now if you add W1 and W2, so that means X1 0 plus X2 0. So how you gonna get the addition? X1 plus X2 0. So is it closed under addition or not? The result is belonging to W or not? Tell me.
Yes, sir.
Yes. Why is it so? Because X1 and X2 are real. If your addition is also real and the second component is also 0. So this is in the same bag, right? Okay. So if you take alpha W1, so that means alpha X1 0. So this will come out to be alpha X1 and 0. So it will also go in what? W, right? Are you with me on this?
Yes, sir.
Okay, so therefore W is a subspace of R2. Is it fine? So let's say if I take W, instead of W, I've taken the set U, which should look like 0, Y, Y belongs to the real. So will this be a subspace of W? R2?
Yes, sir.
Yes, sir.
On the similar line, we can prove that, right? So similarly, we can prove that U is a vector space, a subspace. U is a subspace of R2. Okay, let's take another example. I take W dash, which is all xy such that x is equal to y. All xy such that x is equal to y. Right? So is this a vector space? Let's try to find out this. And again, the condition is same, that your x and y belongs to the real. So let's try to find out this. So let W1 and W2 belong to the W dash. So W1 is what? W1 is something like x1, y1, right? And W2 is what? X2, y2, such that x1 is equal to y1 and x2 is equal to y2. Now, if you take W1 plus W2, that will be x1 plus x2 and y1 plus y2. Now, tell me, this addition will fall in W or not?
So it will fall.
It will.
It will. Why is it so? Because abscissa and ordinate should be same. So in this case, abscissa and ordinate are same or not? Yes, they are same.
Same.
Why? Because x1 is equal to y1 and x2 is equal to y2. So if you add these two sides, so this will also be there, right?
Yes,
So
sir.
therefore, W1 plus W2 is also having the same property. So that why it will fall in W dash. And if you take alpha W1, that means alpha X1 Y1, that will be alpha X1 alpha Y1. So that will also belong to the W dash. Why? Because if X1 and Y1 are same, that means alpha X1 and alpha Y1 are also same. So W dash is a subspace of R2, right?
Yes, sir.
Yes, sir.
Okay, let's take another set, W double dash, that is xy such that x plus y is equal to 1, right? And x and y are real. So is this a vector space of R2 or not? Take W1 which is equal to 0, 1 and take another element W2 which is equal to 1, 0. So they both belong to the W dash or not?
Yes,
W
sir.
double dash? Yes? Tell me.
Yes, sir.
Yes,
Why
sir.
is it so?
Because for W1, 0 plus 1 is equal to 1 satisfy
Yes,
the condition and they both are real.
yes. Because if you take the sum of the abscissa and the ordinate, it will come out to be 1. So it should be closed under addition and scalar multiplication, right? If it qualifies to be a vector subspace, then it must satisfy the properties of addition and scalar multiplication. Yes.
Yes, sir.
But if you take W1 plus W2, see what will happen. 0, 1 plus 1, 0. So that means 1, 1. So now,
Does it belong to W double dash? The answer is no.
why is it so? Because now if you add abscissa and the ordinate, it will come out to be 2, right? So now addition is not going to the W double dash. So that means your W double dash is not a subspace. Right?
Yes, sir.
Yes, sir.
Okay. So I'll combine all examples. How? See this. Determine all proper subspaces of R2. Right? Write down the all proper subspaces of R2. So now, if you look at R2, what is your R2? This was your R2? Yes?
Yes, sir.
Okay. So, see the first space which we have done. The first one is what? W. And that is what? X0 is what? X axis, right? Y is 0, Y is what? Y axis. X is equal to Y is what? The line passing through origin. So our first subspace was this thing. This was our W. And this was our second subspace. Right? And this was what? Our U. And then we have another subspace which was something like this, and this was our double dash. Right? But the thing which was not our subspace was x plus y is equal to 1. So something like this. Right? Is it fine? Right. So that was
What about W
W
dash?
double. Sorry, W dash. Okay, thanks for telling me. Right? Is it fine now? Yes.
Yes, sir.
Now, W dash was not a subspace. It was not a subspace. Right? So can you see anything common between W, U and W dash?
So passing through origin.
Yes, they all are passing through origin, right? So actually, if you see that all the subspaces, all the proper subspaces, I would say, why it is proper? Because there are two trivial subspaces, and they are what? If you take 0, 0 identity element, or if you take R2 complete, then they are the subspaces. We know that, right? That's what we have done in the definition as well, definition of the subspaces. These two will always be the subspaces. Set itself will be the subset of this, and only identity element will also be the subspace. So all the proper subspaces of R2 are nothing but all the lines passing through the origin. Is it fine? So that point actually highlights the necessity of origin as well. Means if you don't have the origin in your set, then this set cannot be a vector space. So if any set which doesn't have the origin, if the origin is not satisfying, right? If the origin is not satisfying, so that means the set doesn't deserve to be a vector space, so vector subspace, right? So if you see this, if you see in our third example, that x plus y should be equal to 1. So you can straight away discard the possibility of w dash as a subspace. First of all, check 0, 0. And if you put 0, 0 over there, so that means 0 plus 0 is not equal to 1. So therefore 0, 0 does not belong to w dash. So you will simply say that if identity is not there, so therefore w dash can't be a subspace, right? Yes, you're with me? Yes, tell me, you're with me?
Yes, sir.
Okay, so the point I want to make is the subspaces, I mean, you can view the vector space as a king, and the subspaces are just like the prince, and prince is having the same kind of authorities as the king possess, but somehow they are still smaller as compared to the vector space. Is it fine? Are you with me on this?
Yes, sir.
Yes, sir.
Okay, so we'll do few more example in our upcoming lectures. I want to give you an exercise. Determine all proper subspaces of R3.